Alright, so we want to finally take a look at some 3 examples here and see which of the theorems, the big deal theorems apply and whether they help me working out the various integration problems here. So the first is the integral of f dr over curve C. F is a two-dimensional vector field, 2x y to the third plus x cosine x, 3x squared y to the third times minus sine of y e to the x. C is the closed curve given by the boundary of a square, like this, with these corner points right there, minus 1, minus 1, minus 1, 1, 1, minus 1, and 1, 1. Alright, C is the flux integral over a vector field f of xy as given here. And S is the sphere of radius 3, centered at the origin. And the last problem is the work integral again, where f is a two-dimensional vector field as given here. C is the boundary of a surface given by z is equal to 1 minus x minus y, restricted by the coordinate planes and it's oriented counterclockwise. So by that I mean the entire surface that has the coordinate planes as boundary as well as the z is equal to 1 minus x minus y. Alright, which theorem applies where? Well, let's take a look at the first problem. The first problem is a work integral. It's a two-dimensional work integral. So every time I think about two-dimensional work integrals and I have a closed curve, which I do here, I know that this is going to be the Green's theorem that I can try here. So let's set this up with Green's theorem and see what happens. So Green's theorem would be saying that I can use this integration here over the closed curve C f dr, and this comes out to be the double integral of dn dx minus dm dy dA in this case, over this square with those corner points. What's the dx now? The dx is y to the third. The dx derivative is 2 times y to the third plus x plus cosine of x. Oh, no, this is of course wrong. Sorry. This is m here. This is n, so I got to take the y derivative of this here minus the x derivative of that. The x derivative of this minus the y derivative, the x derivative of n, which is the x derivative of n. The x derivative of n is 6xy squared. This is y, so that goes away, minus the y derivative of m. The y derivative of m is 6xy squared. So nice, this worked out to be easily 0. No problem about this. Which of course means that this vector field here is conservative, but like we said in class, you don't have to worry about checking whether it's conservative separately because Green's theorem makes this pop right out. Green's theorem. Very good. The second integration is a flux integral, so we think in Stokes' theorem here perhaps? Oh no, what is it, Stokes or Gauss? Right, for the flux integration it's Gauss' theorem, for the work integral 3D it's Stokes' theorem. So that means this is the flux integration, so I want to try Gauss' theorem, so that means I want to try that, I want to write this as f dot n ds works out to be the triple integral of the divergence of f dv over this q. Let's see, what's the q? Q is the sphere of radius 3. This is okay. This is a closed sphere. This surface is the boundary of that sphere, so that's all perfectly correct. And let's find out the divergence of this guy here. The divergence of this guy is the x derivative of the first component, 1. The y derivative of the second component, 2. The z derivative of the third component, plus 3 dv, so I'm going to get 156 times the triple integral of dv, but that's just the volume of this q, and that means that the volume of the q is the volume of this two-dimensional sphere with radius 3, which is going to be 6 times 4/3 pi, and r is 3 cubed. So again, this worked out nice and easy. If I use the right theorem here, then I can work out this flux integration in my head. I don't have to even use Wolfram alpha. Very nice. Let's finally fix up the last problem. The last problem is this work integral of a 3D curve over a 3D curve. So I could try Stokes theorem here. Let's see what Stokes theorem says. Stokes theorem says that I have the integral of f dr over this curve C being equal to the double integral over the surface S, the flux integration over the curl of f dot n ds. So here it becomes the problem to work out the curl of this thing, z squared x squared y squared. Let's work it out. Let's work it out in the next slide here. So I have the curl. Working out the curl means I have to put on the I, j, k as usual, dx, dy, dz, and I have the z squared here, the x squared, and the y squared, and this is cooked up so that the curl of this comes out to be what? This guy is the y derivative of this, which is 2y. The z derivative of this is nothing. Second component is the x derivative of this, which is nothing. Z derivative of this, which is 2z, and the minus 2z, but another minus because it's a middle term here. It's just a 2z. And the k is going to be equal to the 2x minus nothing, so it's 2x. All right, the surface, on the other hand, is given by 1 minus x minus y. All right, 1 minus x minus y. So this gives me, this is equal to what? This means that the curl of the double integral over the curl of f dot n ds over the surface S becomes the integral over the curl 2y, 2z, 2x dot the normal, which is minus fx minus fy minus fz, but this is the function f here. So minus, this is 1 and 1, there we go, minus fx is 1, minus fy is 1 as well. So that means I have a 1 here and a 1 here and a 1 here. dA. So this comes out over this A, and I have to figure out over this D, and I have to figure this out later, in a second. In fact, let's figure this out now. So now what I have is the tricky part here. So this gives me 2z plus 2x, so 2 times x plus y plus z. This is going to be equal to the double integral over the d 2x plus y plus z dA, and I have to figure out how this surface looks like. This surface is 1 minus x minus y. So if z is, this is z. If x and y are 0, z is 1. If x and z are 0, then y is 1. And if z and x are 0, then if z and y are 0, then x is 1. So it's this surface here, like this. That means I have to find out at the bottom is this triangle here. That means that this turns out to be the double integral of two x plus y plus z dy dx. The x goes from 0 to 1. And the y goes from 0 to this line, but this line is the line that I get when I take the z equal to 0, that's equal to x, y is equal to 1 minus x, or x equal to 1 minus y. But since I have a y here, I can use the variable x, so it's going to be 1 minus x. In this, I can plug into Wolfram Alpha to get the answer. All right, very good. So worked out the three examples of the three big integrals by the means of some examples. I should be golden now. Thank you.